Hi everybody. In this last lesson we're going to learn how to put it all together. You might recall in our first video we learned that vectors had magnitude and direction and how we had to arrange them in order to find the sums of vectors. Then in the second video we learned about how we used the trig laws, sine, cosine, and tangent, as well as the Pythagorean theorem to figure out the magnitudes of resultants of vectors. And in the third one we talked about breaking vectors down into their components. Well, in this one we're going to put all those pieces together and see when you might need to do that. So we're going to talk first about using components to add vectors. There are a couple places where you might need to do this. The first one would be when dealing with motion in two dimensions. In the lesson where we're bringing this up, we're dealing with projectile motion, where things are going to be moving in two dimensions at the same time. And since we have so many different motions, we needed to be able to break them into their pieces. So for example, suppose we've got a football sitting on a tee and it's going to be kicked. And the place kicker comes up and he's going to kick the ball upward with some original velocity v0 at some angle theta. Well, if we need to analyze the upward and downward motion, not all of that velocity is in the up and down motion. So not all of that v0 velocity is going to be affected by gravity. Likewise, not all of that v0 velocity is going to be making the ball move down the field. Only parts of it are. The components are. So if you kick this ball and it goes flying off, we can break this into its upward component and its horizontal component. The horizontal component we're representing with that red arrow there. We call that v sub x because it's the component of velocity that's in the x dimension. And the yellow arrow we'll call v sub y because it's the component of the velocity which is in the y direction. Now, when analyzing motion, remember that in the horizontal dimension, in the x dimension, there is no force acting to change that velocity. So once we know what the component of velocity is in the x dimension, we've really only got one equation that describes that motion, because it's constant velocity motion. And that was that average velocity is equal to change in displacement divided by time, or v is equal to delta x over t. Well, when analyzing two-dimensional motion, the velocity now is not that original velocity that we were given, but the component in the x dimension. So we could think of this then as, instead of just v is equal to delta x over t, as v sub x equals delta x over t. So it's the component of velocity in the x dimension that is governing that horizontal motion. Some people like to write this in another form. Remember that that horizontal component is found by taking the original velocity times the cosine of the angle. Well, we could substitute that in as well, and a lot of times you'll see this written this way, and some people prefer it to just write this equation as v0 cosine theta is equal to delta x over t, because remember v sub x is equal to v0 times the cosine of theta. If we look at the vertical motion, remember the vertical motion of a projectile is accelerated because gravity acts in the vertical dimension. So our equations here, again, instead of just dealing with the whole original velocity, we deal with just the original component of velocity that is in the vertical dimension, v sub y. So our basic kinematics equations then, we had one that said the final velocity is equal to the original plus acceleration times time. Well, now the original velocity isn't that v sub naught, it's the v sub y, just the component of velocity that acts in the vertical dimension. So we could think of this equation then as v sub f is equal to v sub y plus gt. And then just like we did over on this other side with the red equation, some people prefer to think of that v sub y expressed geometrically in terms of v0. And since vy is equal to the original velocity times the sine of theta, that would just become v sub f is equal to v0 sine theta plus gt. We also had this equation describing the distance something travels when accelerating. So in this case, the location in the y-axis would be equal to the original velocity times time plus 1/2 gt squared. Well, again, the original velocity now is actually v sub y. So when we put that in, this just becomes y is equal to vyt plus 1/2 gt squared. Or again, we could express that upward component in terms of the original velocity and write it as y is equal to v0 sine theta plus 1/2 gt squared. And then finally, our last one, we had one describing velocities of accelerating objects, where the final velocity squared of some accelerating object was equal to its original velocity squared plus 2 times g times the distance traveled in the y dimension. Well, just like we did before, we can substitute in v sub y, and it becomes v squared equals vy squared plus 2gy. Or if you prefer to express your v sub y in terms of the original velocity, then it's just the final velocity squared is equal to v naught sine theta squared plus 2gy. Now, the other place that you might need to use this stuff is if you're adding vectors that are not originally perpendicular. It makes life a lot easier. Let me show you how. Suppose we've got to add these two displacement vectors. 212 meters at an angle of 27 degrees north of east, and another displacement vector of 78 meters at 80 degrees north of east. Well, we know that to add them, we've got to arrange them head to tail, like this, and the resultant then goes from the tail of the first up to the head of the last. So our goal is to figure out what is the magnitude and direction of that red vector. But we're kind of stuck here because this triangle that we've got is not a right triangle. That means the Pythagorean theorem doesn't apply to it. Sine, cosine, and tangent doesn't apply to it. So about the only way we could approach this, we could draw everything out to scale and just physically measure it. But using components, there's an easier way. For example, if we pull this yellow vector out of here, and let's break it into its components. That vector is headed east and north. So how much of it is east and how much of it is north? Well, here's the eastward component, and here is the northward component. And notice that makes a right triangle, so we can find that eastward component as being 212 times the cosine of 27 degrees, which is 188 meters. Likewise, we can find the northward component by taking 212 times the sine of 27 degrees. That's 96.2 meters. So that yellow vector actually goes 188 meters east and 96.2 meters north. Then let's do the same thing with that light blue vector. Let's find its components. It's got an eastward component and a northward component, and we can find the eastward component by taking 78 times the cosine of 80 degrees. That's 13.5 meters. We'll find the northward component by taking 78 times the sine of 80 degrees. That's 77 meters. Now, rather than adding the two original vectors, let's deal with their components. So we put the two horizontal components, the two x components in, and that's actually a total of 201.5 meters then to the east. Then let's put the two y components in, the two northward ones, and that's actually a total of 173 meters to the 0.2 meters to the north. Now notice that we're dealing with a right triangle. Now all of our other tools are useful again. We can use the Pythagorean theorem to figure out the magnitude of the resultant vector. We can use one of the trig laws to figure out the angle it's pointed. So for the magnitude, that's just 201.5 squared plus 173.2 squared equals square root. Pythagorean theorem. That resultant is 266 meters long. To figure out what angle it's pointed, we now have all three sides, so we can use any trig law that we want to figure out the angle. For this purpose, I just selected tangent because I've got the opposite and adjacent sides showing on the screen already. So if we use tangent, the angle is going to be equal to the inverse tangent of opposite over adjacent. That's the inverse tangent of 173.2 over 201.5. That angle is 40.6 degrees. And so there we have it. We've got the final resultant. That red vector is 266 meters long, and it's pointing in a direction of 40.6 degrees north of east.